All right, we are continuing our series for question 5. We want to finish up question E. We also want to get to the bottom line of question F, question G, and question H. So let me just write down E and see how it goes as well. So E is saying there's a double bond to oxygen there. We're having a ring. Okay, great. So we have our first reagent as sodium cyanide, and the second reagent we're having is sulfuric acid in the presence of what, and also the presence of water is there. So the first step is we want to predict the major product that we're going to get from this reaction in the presence of the reagents that have been given here. So let's predict the reaction mechanism. That's mechanism. So the reaction mechanism is very easy. We are having the sulfuric acid. The reason why we're having the sulfuric acid is for us to activate our reactant. So from the sulfuric acid, we're going to get the proton. There, this will split, and then we're still going to have the HSO4. Okay, and this proton is positively charged, and then we're going to have an attack from the carbon, attacking the what? Attacking the hydrogen. And when that attacks, we're going to have the carbon, we're going to have the oxygen being bonded to the hydrogen. So after that, we're still going to have, I'll continue from here. We're going to have, we still have that OH there. Okay, we still have that as well. And then after this reaction, we remember that we have just activated that and we have added the hydroxide to the compound. Then we have the sodium cyanide, NaCN. And the sodium cyanide, you know that the sodium is positively charged or the cyanide is negatively charged. So we're still going to have something like this is Na, this is positive, and the Sn is negative. And then we know that this part here, which is the carbon connecting to the hydroxide, is what? Is positively charged. So we're going to have an attack there. This is going to attack here. And when it attacks, we're going to have something like this. We're going to have attachment of the cyanide. And when the cyanide attaches, we're going to have this structure right there. So let me use a different color to show you what's happening. Okay, so we're having attack from the cyanide attacking the carbon there, and when it attacks the double bond that is there, it will break, taking the number of electrons to the hydroxide. So we're going to have that. We're going to have a single bond there, 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 there. Then we're going to have the cyanide attaching. This cyanide, I'll just write it in this form. It is a triple bond to the nitrogen with the two lone pairs of electrons. So since we're having the two lone pairs of electrons, the water will come in to take the two electrons there. We know that this proton here will come and get these electrons. And when those electrons are collected by the proton, this is going to come there. So the nitrogen is going to attach to the what? To the hydrogen. So this becomes our structure. We're going to have OH there. Our ring remains the same. Then we're going to have the carbon. This is no longer going to be a triple bond, it becomes a double bond because of the attack to the nitrogen, and the nitrogen is now bonding to the what? To the hydrogen, and that becomes our final answer. So we have an amine there. So the reaction mechanism for this is very easy. The reason why we're having the acid and the water there is to make sure that we activate the reaction, and after activating the reaction, we're making it very possible for the cyanide now to react in such uh, at this point here. When it reacts, and then you proceed to come here, attachment of the cyanide, and then the water will come here, will come in to attach the nitrogen, breaking the triple bond that is between the carbon and nitrogen, the cyanide, and then you are going to have the secondary amine being produced as end product. So that is how it works out. Let's look at a different question. The other question we're supposed to look at there is question F. We're having F, and F was this product. In the previous video, I gave out the reaction mechanism for the Grignard reagent. So we're having that. So under the Grignard reagent, it's very easy. The reaction mechanism is actually very easy. I'll just explain it. So we're saying that the first step, this carbon here is going to attack the car. It is going to attack the carbon that is double bonded to the oxygen. Why? Because you know that this is a metal, and this metal is positively charged. Okay, this metal is positively charged, and this is because this metal here is more positively charged than the carbon. It makes the carbon negatively charged, and the carbon is going to attack here because this is positively charged. So this is negative. The carbon here is negative now, going to attack the carbon which is what? Positively charged, breaking the double bond there. So we're going to have attachment of the CH3 in the absence of the what? In the absence of the MgBr. So you're going to have the structure here. You have it. The other structure comes through, and then this is going to break. You're going to have bond there, 1 2 3 4 5 6, and this becomes negatively charged, and at the other point you're going to have attachment of the CH3. Okay, so one thing that we must note here is that we can't leave this structure like this because this is very reactive. So we're going to introduce water so that it picks up the hydrogen. So the oxygen is going to attack now the pair of the hydrogen, so that this number of electrons come there, so that it becomes very stable. So our final product now becomes this. Okay, so we have OH here, and then we also have CH3. So that is how you write out down the reaction mechanism for that. So I want you to note something here, that this is a chain elongation reaction. It just makes the chain a bit longer because you're going to have now another carbon chain that is here, and this carbon chain is the methyl group. So the CH3 to the MgBr is more negative. Because this is more negative, more positive. If this is more positive, this makes the CH3 negative, and because the CH3 is negative, this is positive. It's going to attack there, breaking the double bond, and then we're going to have attachment, and that is how the reaction proceeds. As easy as that. Let's go to G. We want to proceed to G. So G is also very easy. So G, the structure that we're given is this. We're the ring. Alright, then we have that. So we have in a ketone there. And then we're having CH3OH. And then we're also having the proton. Okay, so the presence of the proton, I think we know. Like from the previous reaction that we just did, the proton there is that to activate. So we're just going to have our first attack. The proton is going to attack. You've seen that, right? The oxygen is going to take up the proton, and when the oxygen takes up the proton, we're going to have the OH be attached in there. So we're going to have this structure. There we have it. There we have it. There we have it. There we have it. Then we come there. Come there. The double bond still remains, and then we're just having attachment of the what, of the hydrogen, having the hydroxide there. So remember that we still have CH3 there, OH, and the CH3OH is there. This is more negative. It is going to come and attack at the point where we're having the carbon double bond to the hydroxide. It attacks right there. After that attack, we're going to have this. This is that. This is that. And that's that. Breaking the number of electrons here, bringing them here. 2. This now becomes OH. Then this becomes that. Let me write that properly. This is OH. It was a double bond. It has now become a single bond because the bond was broken because of the attack that was coming from the CH3OH. So that attaches. We still have a bond there, and then you have attachment of the OCH3, and also this is also attached to the hydrogen. That is how it works out. And then we're still going to have the CH3OH, which is still in the compound, picking up the what? The hydrogen. And this number of electrons will remain there. And our final product now is this. We just had a proton shift. That's an intramolecular reaction. An intramolecular reaction. We're having that, we're having that, we're having that. There we go, there we go, there we go, there we go. OH. Then we're having OCH3. The OCH3, we're not having the hydrogen because the hydrogen has been picked away by the CH3OH, which is in the compound. And this becomes your final product. So the reaction is as easy as that. So the first step was where we're getting the proton, and the proton is the hydrogen attacking the oxygen. Attacking the oxygen to make that reaction start or activate it. And then we're going to have this CH3OH, this alcohol here, now attacking the carbon to oxygen bond, breaking it, and then we're going to have those attachments, and that is how we got here. So this is how the reaction mechanism proceeds. Let's look at the last question. And the last question is H. H is quite easy. You just have that, which is double bonded to that. Then you still have OH in the presence of what? PCC. So we've already looked at the reaction mechanism for PCC. It's actually very easy. So I'll just give you the end products. So now let's identify what we are having in this question. So in this question, we are having an aldehyde. Okay? And the other thing we're having here is the alcohol. So the alcohol in the presence of the PCC, what are we going to have? And what kind of an alcohol is this? This alcohol is a secondary alcohol. So now, since we have a secondary alcohol and we also have the aldehyde in this reaction, how is this going to proceed? So the PCC is an oxidizing agent. It is going to oxidize the secondary alcohol. So I'll mention that this is a secondary alcohol. It is going to oxidize the secondary alcohol to a ketone. How about the aldehyde? The aldehyde with the reaction, the aldehyde react with PCC. So that reaction doesn't take place because we are only trying to convert the alcohol to the ketones or the aldehydes using oxidizing agents such as PCC. And we can only take the aldehydes to the alcohol through a reduction method. And right now we are only having PCC. So PCC, there's no reaction that is going to occur at this point. This point right here, there's no reaction that is going to occur. That product will still maintain. So our end product is just going to be that. One, two, three. The ring is still going to maintain. Then our focus point is while we're having the alcohol. The alcohol now going turn into what? To turn into a ketone, because we are saying that PCC is able to it's an oxidizing agent that is able to oxidize the secondary alcohols into a ketone, the primary alcohols into an aldehyde. So conversion of an alcohol to an aldehyde or a ketone is through PCC as the oxidizing agents and other oxidizing agents such as the Jones reagent. And then conversion of the aldehydes to the alcohol, that is why we use reducing agents such as the aluminium hydride, aluminium borohydrides, and so on and so forth. So this is how you're supposed to look at question 5. Thank you so much for your attention. We look forward to interacting with you in question 6.